When you drop an object, it falls in a straight line toward the center of the Earth. When you place two static charges near each other, they pull or push along a direct path. We are accustomed to forces acting in simple, predictable lines toward a source. Magnetism breaks this intuition. If you fire a charged particle into a magnetic field, it does not move toward the magnet. Instead, it veers off axis, pushed perfectly sideways into a curved trajectory. By the late 19th century, physicists realized these results represented a new mathematical requirement rather than a failure of their measurements. The definitive solution came from Hendrik Antoon Lorentz. He formulated the complete law describing the interaction between charged particles and electromagnetic fields. This is the Lorentz Force equation. It contains two distinct parts, one term for the straight-line pull of electricity and a second term for the sideways push of magnetism. To understand the sideways push, we have to isolate that magnetic term, Q times the quantity V cross B. The magnetic force remains distinct from other common forces because it is entirely dependent on the geometry of motion. In this equation, Q represents the electric charge. A particle with no net charge, like a neutron, remains unaffected by magnetic fields, passing through them without experiencing any force. The variable V creates a specific condition. The particle must be moving to feel a push. If velocity is zero, the magnetic force remains at zero, regardless of how strong the surrounding magnetic field is. As soon as the particle enters motion, the magnetic field exerts a force. A vector appears, pointing 90 degrees away from the direction of travel. This characterizes the magnetic force as dynamic, appearing only while a charge is in motion. Magnetic fields interact exclusively with targets in motion, acting as an active environment for moving energy. The X symbol in the equation represents a vector cross product. This operation functions as a three-dimensional geometric instruction, taking two vectors and outputting a third that is perpendicular to both. This math enforces the parallel rule. If a charge moves in the same direction as the magnetic field lines, the result of the cross product is zero. No push occurs. The force reaches its maximum only when the particle cuts across field lines at a perfect 90-degree angle. We visualize this math using the right-hand rule. Your thumb points in the direction of velocity, your fingers follow the magnetic field, and your palm shows the direction of the force. This specific orientation applies to positive charges, such as protons. Electrons have a negative charge, or a negative Q. In the math of the cross product, this negative sign forces the resulting vector to point in the exact opposite direction. This divergence means a beam of mixed charges will split into two opposite curves upon entering a magnetic field. Scientists use this exact principle in cyclotrons to guide and accelerate particles at nearly the speed of light. Because the cross product always pushes perpendicular to the direction of motion, it creates circular and spiral paths rather than straight lines. Because the Lorentz force is so consistent, it is used to define the standard unit of magnetic field strength. Imagine a charge of exactly 1 coulomb moving at 1 meter per second, perfectly perpendicular to a magnetic field. If that charge experiences exactly 1 newton of force, the field strength is defined as exactly 1 Tesla. Tesla is the SI unit of magnetic field strength. SI stands for the International System of Units. The unit is named for Nikola Tesla, a pioneer of electrical engineering. A single Tesla represents a massive amount of strength. Earth's magnetic field is a tiny fraction of a Tesla, while powerful MRI machines use several Teslas. MRI stands for magnetic resonance imaging, a medical technique that uses strong magnetic fields to visualize internal body structures. Each Tesla of strength measures how much sideways force a field can exert on a unit of moving energy. A magnetic force only exists when 3 requirements are met. There must be a charge, that charge must be in motion, and it must travel across the field lines. This interaction allows us to harness electricity and understand the motion of plasma in distant stars. While electricity and magnetism appear distinct, physicists like James Clerk Maxwell and Lorentz proved they are manifestations of a single electromagnetic interaction. The vector cross product generates the curved trajectories of moving charges throughout the physical world.